Hello everyone. So today we're going to talk about 6.5 curvilinear coordinates. So in you probably recall learning in calculus, one of the things that we need to do in calculus is to calculate area and volume using integral, which is where we're heading into in chapter 7. So and you probably remember learning it in BC calculus, where if you are looking for an area or a volume of a certain regions, it's sometimes beneficial if we are using a coordinate system that would actually work well with the regions that we try to calculate the area or the volume. And you actually learn one such coordinate system called polar coordinate system, which actually allow you to deal with things that move in a circle versus then things that move in a straight line. And when we allow us to actually change the coordinate system that we use, we do something that's called coordinate transformation. So what is a coordinate transformation? A coordinate transformation, there you go. A coordinate transformation is just like a transformation, which is basically a function that maps from Rn to Rn. So we call a function f that maps from Rn to Rn is called a transformation. The reason why I call it transformation because it basically keep a vector in Rn to replace it with a new vector in Rn, and by doing so, kind of change the shape of the image that you're drawing. So if you're taking a regions in R2, suppose something like this. Let's say, for example, you have a shape in R2, and then after you go through the function f, and you still maintain in R2, but now you have a different shape, then that's what we refer to as a transformation. Because transform from one, the domain into the image, where they both have the same dimension, but just have different shape. A very special kind of transformation is called coordinate transformation if this is true. If the transformation is 1-to-1 and has an inverse, then it is called a coordinate transformation. And a coordinate transformation basically just means that it changes the coordinate that we use to describe the position. So the position can remain the same, but it just being used now using a different coordinate to describe it. One such coordinate system is called a polar coordinate system that you remember, instead of using an x and y value, which is basically how far you move left and right versus how far you move up and down. Instead, polar coordinate system using a distance from the origin, or actually called the pole, and also a rotation angle to define the same exact position as x and y. Important to understand is that this coordinate transformation has to be 1-to-1 and has an inverse. It has to be 1-to-1 so that the coordinate can remain to be unique for a specific position. If it's not 1-to-1, that would imply that maybe multiple coordinates in one system can map to the same position in another coordinate system, and that would create a confusion. Not to mention, if it's not 1-to-1, it cannot have an inverse. And having an inverse is important because then allow us to go back and forth between multiple coordinate systems. In 6.5, we actually go talk about 3 very common type of coordinate system that I would like you to know. Okay. Oops. In 6.5, we will talk about 3 common types of coordinate transformation. So before we actually get started on each of these three types, first thing is the following. In each case, in each type, we will start with a domain that is a subset of Rn. As a matter of fact, one of the coordinates would be from R2, and then the other two will be from R3. So, but we'll start with a subset of Rn. So for us, as I say, it will be R2 and R3, which we will call U sub n. And that would act as the domain of the transformation. And one interesting thing about these three coordinate transformation is that they often be referred to as curvilinear coordinate system. And yes, the word curvilinear is actually kind of weird because it kind of combined the word curve and linear and line together, and which those two things are kind of polar opposite of each other. And you're correct, they are. So the idea of curvilinear coordinate system is that they are actually coordinate systems that transform lines into curves. So these three coordinate systems are often called collectively or defined as a type of curvilinear coordinates system. Curvilinear. And the reason why, since they transform a rectangular coordinate system, so meaning a system that's formed mainly by straight line, into a coordinates system with curved axes. Oops. So that's the reason why they're called curvilinear coordinate system. So we're actually going to start with one that you have already learned from R2, and that's called polar coordinate system. Oops. Polar. Polar coordinates. So each one of these, what I would like to do is simply to define what is the transformation, define the domain, and also show you how we define the variable, and also probably show you some kind of inverse transformation of it. So for polar, you already know, so I'm going to go and define it. Let t be a function that went from u squared to r squared. And t of r theta is equal to r cosine theta, r sine theta, which is equal to xy. So each of these coordinate transformation will take the polar coordinates and transform it into the xy coordinate system. Now you might be thinking, well then wait, isn't r theta the curve coordinates and then xy is the regular rectangular coordinate system? Kind of true. Let me show you how that works. So before we do that, let's define this first. So t of r theta will equal r cosine theta, r sine theta, and they equal to x and y. So essentially what this basically means is this. That just simply means that x is equal to r cosine theta and y equal to r sine theta, which is basically the typical ways we define polar coordinate system. And I'm going to define the domain with domain u square consists of the following. R go from 0 to infinity, but does not include 0. And theta go from 0 to 2 pi, but do not include 2 pi. Okay? So how do we define these variables, r and theta? Well, r is basically called the radial distance from the origin to the point. To the position that you want to describe. And theta is basically the counterclockwise angle of rotation from the positive x-axis. Oops. So show you a very simple picture to describe. So in the polar coordinate system, the origin is actually called the pole. And then the positive x-axis is actually kind of referred to as the polar axis. Okay, however, we usually do superimpose this on the xy plane using this as using the pole as the origin, and the polar axis is like the positive x-axis, and then we add in the y-axis. So suppose I want to define this one position right here. So how does polar coordinate system describe this position? It will first draw a line that connect these 2 points together, and then define this distance to be r. And then it would define this angle as the angle rotation. So if I rotate angle theta and travel from the pole in that direction, distance r, we'll be able to get to the position that we want to get into. Now, one of the interesting things that students often don't realize is how the curvilinear coordinate system works. So remember, it changes from something that's rectangular into something that's circular. So how does that work? So this is how it works. So if I look at the domain of the function, the domain actually exists in what we call the r theta plane. This is our domain, which is the r2. And the r theta plane would actually be this. So here's 2 pi, and we'll draw a dotted line to indicate it does not include. And then I'm going to also draw a dotted line right here to indicate that r equal to 0, which is also not included. And then here is our domain. It's actually an infinitely long rectangle with 2 of the boundary missing. And the function t actually will transform this into the xy plane, where it actually form a circular region. I cannot actually draw that. The reason why I cannot draw that because it actually covers the entire xy plane. But I could do the following. Imagine I define a specific r sub 0 value and a specific theta sub 0 value. Then that would define this unique point right here, which is r sub 0, theta sub 0. And now what happened is this. So here's where the curvilinear is supposed to come in. So the r equal to 0, when I transform it through t, it actually forms a circle. And then the theta equal to 0 would actually transform into a radii. And then the intersection between these 2 curves define the point r sub 0, theta sub 0. But of course, that would be now referred to in the xy coordinate system. So they're not equal, but transform into. So that's how the curvilinear coordinate system works. So the interesting thing that for students often get confused about is that notice that in the r theta, you actually have straight line. But those straight lines actually turn into curve in the xy coordinate system. Now, the last thing I want to show you will be following would be the inverse transformation. So the inverse transformation is called T inverse. It's basically this. Is an inverse function that when you plug in x and y, you can actually construct r and theta from it. So basically, this basically say r is equal to the square root of x squared plus y squared, and theta is actually tangent inverse of y over x. Now, with something that's very important is the following. Something, make sure that you write it down. In this case, something important that you have to write down. The inverse tangent must put theta into the correct quadrant. So you have to actually do a little bit of work to make sure that you get the theta angle correctly. With the inverse tangent suitably defined to put theta in the correct quadrant. The reason why you have to have a little disclaimer here is because inverse tangent only actually give angle from negative power 2 to positive power 2, but here theta can actually be anything from 0 to 2 pi, so you're going to have to do a little bit of work to try to make sure that you get the theta in the correct angle. So once you do inverse tangent of y over x, you have to actually figure out what quadrant theta should be in and change that angle into an angle that's between 0 and 2 pi. So this one is a polar coordinate system. So this is how we define the two coordinate r and theta. And this is how the domain, and this is, I guess I should say, the image. So that's the coordinate system that you catch it familiar with. So now we're going to move on to the next one. The next one you probably have never heard of, but yet you probably should expect that we're going to talk about. Is the following. So polar coordinate system can allow us to deal with things that move in a circle. But you do realize that we live in a three-dimensional world. And the problem is, even though we're living on the tangent, we feel like we're living on the tangent planes of a sphere, but realistically, we are living on a surface of a sphere. Unless you believe the Earth is flat, then that's different. But don't worry, even if you believe the Earth is flat, we have a coordinate system for that too. Okay, that's we will talk about that too. So since we do live on a sphere, on the surface of a sphere, though, it's probably a good idea to understand how to define coordinates on a sphere. And you actually kind of know because you probably learn how to define a coordinate or position in space using latitude and longitude. So we kind of define something similar. Notice that both of those things are actually angles. And since we are on the surface of the Earth, therefore we have a fixed radius. And that basically defines the three things that we need to define what we call spherical coordinate system. So as the name suggests, it's talk about sphere. So I'm going to try to basically present the coordinate system the same way, just like this. The only thing that I would not be able to do is show you how the image will look like. The reason why I won't be able to do that, because in the case of polar, I can define these two as line, and then they will form curve. But in the R3 scenario, if I fix any one variable, it actually forms planes. So it's very hard for me to draw them to show you. I can still draw the domain, I just won't be able to draw you what happened if I fix the coordinate individually and what happened to it. So let's define the transformation. So I'm going to let T stand for the transformation that go from U3 to R3. And this transformation taking three things: R, phi, and theta. So these last two are angles, obviously, and R actually kind of stand for radius. And here's how the coordinate system works. And the domain U3, which defined by the following. So R, as I say, is kind of like the radius. Phi is actually the angle. If you want to think about it as like on Earth, then phi is actually the angle that rotates from the North Pole to the South Pole. And because of that, it actually go from 0 to pi only, because it'll go from North Pole to South Pole. And theta, you can imagine that as the angle rotation around the equator, which actually go all the way around from front to back. Therefore, it's go from 0 to 2 pi. Now, what are these three things? Then I'm going to try to define them for you. So let me see how I did that. Okay, so I did like that. Okay. So I'm going to define these three things for you. So suppose here is my R3 space, a typical R3 space defined by X, Y, Z. And let's say I define one position right here. Here's my position that I want to describe. So how does a spiritual coordinate system describe this position? So first, R is basically the radial distance from the origin to the position. So notice that is the same definition as in polar, except that this distance actually not on the XY plane, but actually in R3 space, from the origin to the position. So what I'm going to do is I'm going to define that. I'm going to try to do the same thing kind of like what we did here. Okay, so I'm actually going to use three different colors to describe it. So let's start with this one. So this is basically what R is. So it's how far from the origin to the position. Then what is phi? Phi is basically the angle of rotation. Is the angle of rotation from the positive z-axis to the negative z-axis. So it basically rotates from top to bottom. So in this case, the angle of rotation will basically go from z-axis, rotate down to this R line. Oops. And that's what phi is. Now then, what is theta? Theta is the angle of rotation also but here's a different part. But it's the angle of rotation on the XY plane from the positive x-axis. Notice that theta is defined the same way as the theta in, oops, sorry, wrong symbol. The theta is the same, defined the same way as in the polar coordinate system. From the positive x-axis, going counterclockwise. There. Now, but then of course, the problem is how could I rotate theta on the XY plane while this line actually is not on the XY plane? Well, this is how they work. So what happened is, to form angle theta, what you first have to do is basically take this position and kind of look for its shadow, which is basically what we call the projection. So I'm going to define this point right here, which we call this the projection of the position onto the xy plane. And then we define a line that's on the xy plane that go to the projection. And then I can now define the angle theta, which is the rotation from the positive x-axis to the line. Now, something interesting that I do want to point out is the following. If you look at this picture, notice that this red line is R. Now, we can actually identify the distance, the vertical distance from the projection to the position, as well as the rotation, the distance from the origin to the projection. And the interesting thing is that actually the projection and the line on the xy plane would form a right angle. This distance right here is actually the z direction, a z coordinate, which is actually what r cosine phi is. And this green line on the bottom, that is actually r sine phi. And so therefore, I identify this position right here to be r sine phi, cosine theta, r sine phi, I kind of need a little bit of room. Let's see if I can do that. Sine theta 0. And now with this, and then with the z coordinate, the length, maybe I shouldn't call it z, but just call the vertical distance r cosine theta. Now allow me to define this point to be r sine phi cosine theta, r sine phi sine theta, and then r cosine phi. So that's how the coordinate system come about. It's basically the polar coordinate system move up, following basically this right triangle here. The domain actually would kind of look like a rectangular prism. So I'm actually not going to draw it because it's actually look kind of weird if I try to draw it. But your textbook does have a good picture. So if you go to your textbook, you should be able to see a nice picture of it. Instead, I'm going to just define the last thing I want to show you, which is the inverse transformation. So the inverse transformation for fifth spherical coordinate system is basically T inverse of x, y, z. And that's given by this set of function. Square root of x squared plus y squared plus z squared. Cosine inverse of z over r. And then tangent inverse of y over x. Now, the middle one is a little weird because I have z over r. So, but I haven't actually defined what r is. But r is actually what the top coordinate is. So instead of writing out square root of x squared plus y squared plus z squared, I just kind of get lazy and just write r. So you should understand. Now, in here, it's the same exact problem. You have to make sure that your tangent inverse give the correct angle. Now, for phi is actually okay because cosine inverse will actually give an angle between 0 and pi, which is exactly what phi is supposed to be. Tangent inverse give an angle between negative pi over 2 to positive pi over 2, which is not what theta is supposed to be. That's the reason why you have to watch out for. All right. Unfortunately, my time ran out, so I guess I will do the last coordinate system on the next video, as well as what the last thing I want to show you. All right. So that's it for this video, and I'll talk to you again in the next video. All right. Bye bye.